Hey everybody, welcome and welcome to Modern Cosmology right here. This is chapter 14. This is our last chapter in Unit 4, and we're going to try to summarize the key ideas about modern cosmology. Let's take a quick look at what large scale means. We talked about this a little bit before. Cosmology is about the large scale universe, and the large scale means usually means above the scale of galaxies. That means greater than 1 million light years in scale. Remember that galaxies cluster, the clusters of galaxies cluster, and that's called a supercluster, okay? Cluster of a cluster is a supercluster. The supercluster scale is 100 million light years. What that means is that that's the largest organized structure known in the universe. So beyond that, there aren't any real organized structures. And here's the key point here. This is called the cosmological principle. The large-scale universe is isotropic. That simply means it looks the same in all directions. But large-scale universe is also homogeneous. That means it, in effect, is well mixed. The cosmological principle says any observer from any galaxy sees the same large-scale properties for the universe. Okay, that's the key idea. There's nothing special about where we are in terms of looking at the large-scale universe. That's the first thing. And if something is not in one location, that means it probably won't be in another location. That's what homogeneous means. Okay. Now, I want to review a couple of things with you here. One is the Doppler effect, because I'm going to show you the Hubble's law again real quickly and talk about it for you. Doppler effect, this simply means that we measure the shift of a spectral line in a galaxy that's moving away from us, and most of them are. And from just the shift of a spectral line in the galaxy's spectrum, we can easily calculate the velocity of the galaxy. And if it's moving away from us, it'd be a redshift. Keep that in mind. That's actually used to measure the distances of quasars. It's a big deal. Now, subject variable stars we've talked about a couple of times. These objects, by the way, can be seen out to 100 million light years. That is a long way, but it's not to the end of the galaxies. The galaxies go out to billions of light years. And so there needs to be other techniques. If you don't remember Cepheids, you should look them up and review them in the previous videos and PowerPoints. Now, here's a new type of thing we haven't talked about. We can do distances from a supernova type 1a. This is a different supernova than what we've talked about. The supernovas we've talked about are type 2. That's when the core collapses and the entire star creates a supernova. This one has to do with white dwarfs. White dwarfs, remember the death state for sun-like stars? They're Earth-sized and very dense and quite hot. What happens is if they have say a red giant star near them, they can actually suck gases from the red giant star until they get so hot that the whole star begins to fuse and blows up in a supernova type fashion. These, by the way, the type 1a supernova are the brightest supernovas in the galaxy. They're nothing to sneeze at. They're really something else. They can be seen beyond 10 billion light years quite easily. Now, what makes them so useful is that each supernova 1a is believed to have the same peak luminosity, and it's about 10 billion times the sun's luminosity. That's not shocking. A supernova should be big, but what's shocking is that they all have the same peak luminosity, and that makes it real easy. All we have to do is monitor the light curve, how bright the supernova is, until it reaches its maximum. We can assume that's 10 billion solar luminosities. Now all we have to do is measure the apparent magnitude then. And remember, if we compare luminosities to apparent magnitudes, that always gives us a distance. So that's how that game's played. Here's Hubble's law. Now, Hubble's law, remember, is the prime #1 observational data set related to cosmology, that is the large-scale universe. And the message of Hubble's law is that the universe has been undergoing a large-scale expansion for a long time. Now, this shows you a little bit about how that works. Here's spectral lines. Notice the red arrow is pointing to galaxies. This thing's going to bounce back here. Notice that the spectral lines are having a small shift. As the galaxies get further away, the shift gets larger. What that means is if the shift is large, that means that the galaxy has a large velocity away from us. And we can actually use that velocity on the Hubble's law and then go right on down here and measure the distance. So the thing to remember is that the redshift of any galaxy can literally be used to get its distance from us using Hubble's law. Now, here's the Big Bang Theory. The Big Bang Theory was built to accommodate Hubble's law, because Hubble's law says there's a large-scale expansion. The Big Bang Theory says you're darn right there was. There was a large-scale expansion. It started about 13.8 billion years ago. And oh, by the way, space, time, matter, and energy also appeared then. They did not exist before. And that's how the universe started marching off into eternity, so to speak. You can check out the rest of this message here, but those are the key points I want you to take with you. Now, not everybody liked this theory. Here's Fred Hoyle, probably one of the best astronomers in the mid-20th century. He's famous, among other things, for inventing the theory of nucleosynthesis. That's a good word, by the way. That's the word that means the building of heavy elements from things like hydrogen and helium, okay? He and a couple of his pals in the post-war time frame basically came up with this theory that explains how red supergiant stars, produce all the elements in the periodic table up to iron. An enormous achievement, as a matter of fact. He also did not like the Big Bang Theory, and so he created one of his own called the steady state. And the steady state says the universe has not undergone any large-scale changes for its entire lifetime. And oh, by the way, it wasn't born. The universe always has been and always will be. So no large-scale changes and no birth and no end. That's quite different. When they talk about evolutionary theory here, this means the Big Bang. The Big Bang started small, and we can see the large-scale expansion going on here. These dots are galaxies. We can think of them as galaxies. Notice as the universe expands, the galaxies get farther apart. That makes sense. That's what the Big Bang was developed to do, accommodate the large-scale expansion of Hubble's law. But the steady-state theory says it is true. The large-scale expansion is occurring, but notice the galaxies in our universe don't get farther apart. Do not get farther apart, as you can see. Now, the only way that's possible is if there are new materials coming into the universe from outside that eventually form new stars, and enough stars form so that new galaxies can form throughout the history of the universe, okay? And that actually is fair play, because in reality, the Big Bang simply brought everything into the universe at once, and the steady staters simply say, no, we think it kind of dribbled in over the entire history of the universe. That's why our galaxies never appear to get farther apart, because new galaxies form at the rate required to keep them from appearing to move apart. But keep in mind, the large-scale expansion is still occurring for the steady state. It's just that in the Big Bang, there are no new galaxies coming in. Okay, so what we learned is that the steady state and the Big Bang both are compatible with the large-scale expansion. That is Hubble's law. So the question is, what about other observational aspects of the universe? Do they vote in favor of the Big Bang or the steady state? Very important question. Here's a picture of one of the first quasars. You've heard of quasars before. We talked about that in galaxies. This is an actual image, and this is the quasar. You can actually see a jet coming from this thing. And we know, by the way, from measuring the redshifts of the quasar, we know that it's more than 10 billion light years away. Remember, I showed you we could do that. Now the question is, this is a star in our galaxy that's in the foreground. And notice that this is just a regular star, and yet the quasar is about 1,000,000 times farther away than this normal star, and yet it looks even brighter than this star. So this star is burning hydrogen and helium to get its luminosity. But the question, this is back in the 60s that people were seeing these things. The question is, how can this thing be 1,000,000 times farther away and yet be even brighter than a typical star? And of course, we know the answer has to do with supermassive black holes, but they didn't know that back then. This was the first image from Hubble Space Telescope taken in 1996. I showed you this one before too, that shows a quasar actually sitting in a galaxy for the first time. And that made things a lot easier to understand. Here's the way quasars get energy, using a black hole and having an accretion disk composed of gas and dust and maybe torn up stars that got too close. Remember, space is warped around these black holes, and so this material doesn't sit in an orbit forever. It actually comes in and eventually gets sucked up. If you wait, say, 10 million or 100 million or longer years, the accretion disk will be largely sucked up by the black hole over a period of time. And this is the question that people wanted to think about. How do the quasars play in favoring either steady state or Big Bang? To understand that, we need to understand look-back time, which is a real easy concept. The sun sends light to us, and the light takes 8 minutes to get here. So when we see the sun, we aren't seeing the sun as it appears now, this instant. We're seeing it as it appeared 8 minutes ago, when the light left the sun. Now, when we look at things much further away, like, say, galaxies or quasars, let's say we're looking at a quasar that's 10 billion light years away. That means the light takes 10 billion years to reach us from that quasar. So the question is, has the quasar likely changed during the 10 billion years it took the light to get to us? And the answer is, of course it has. Because in 10 billion years, remember, the sun will burn through its entire store of hydrogen and leave the main sequence. So big things happen in that time frame. And so this kind of light coming from a very ancient object doesn't suggest the object is still there. It just simply says that it's probably changed during the time that the light took to get to us, if it's billions of years. Let's take that idea. This is a map of the universe. And actually a real map of the universe showing galaxies, quasars, and the cosmic microwave background, which we're going to talk about next. But the Earth is right at the point. This is like a slice of a pie. The entire universe does this. But we're looking at just one slice of the pie because that's all we need to see. Here's the Earth and the Sun, and notice this is the look-back time in billions of years. Everybody see that? And what happens is, way out here at 13.8, we had the origin of the universe. But the interesting thing is, here's the edge of the regular galaxies and quasars. The regular galaxies go all the way out to about 7 billion light years, and the quasars start at 7 billion and go all the way out to about 11 billion light years as we look back into the universe. Now, the idea is that there are no nearby quasars. You can see that. In fact, the closest one is about 7 billion light years away. That's a long way. And so the question is, the fact that there are no nearby quasars means they probably don't exist, because if they did exist, they would be all through the space that is the universe. And so the question is, why are we seeing these extinct quasars at great distances? And the answer is, it's look-back time. In other words, let's take 10 billion light years again. A quasar radiating toward us from 10 billion light years, the light would take 10 billion years to get to us, and during that time, the quasar would go extinct. And what does that mean? That means that the supermassive black hole in the quasar probably would suck up most of the accretion disk, and so the accretion disk brightness would decline rapidly. So there's the deal, and the question is, well, there's several questions, but we already talked about the observed position of the quasars. They're all beyond 7 billion light years. What does this mean for the evolution of quasars? It means that there are no actual operating quasars in the universe right now. They're all gone. If there were real ones operating now, we'd see them at closer distances. Now, part 3, how do quasars support or oppose the steady state of the Big Bang? There's the real question. And let's take the steady state first. The steady state says, hey, there's been no large-scale change in the history of the universe in our model. And the problem is, quasars formed about 10 billion years ago, and then they disappeared less than that time. And since quasars were the brightest objects in the universe, they clearly are a large-scale change. This is when people started to lose confidence in the quasars. And you'll see the Big Bang doesn't really care because it's neither here nor there from them. But when you've got a theory that says nothing can change, no large-scale change can occur, and then you see one, that's a bad thing for that theory. Here's what the quasars looked like. This is the number of quasars on the y-axis. This is time from the Big Bang to us way out here at 14 billion years. The quasars came into existence, and then it looks like their accretion disks pretty much dissolved their, the supermassive black holes pretty much dissolved their accretion disks and then they went away. That's a large-scale change. Now, the next interesting thing that happened also in the 60s was the discovery of what's called the cosmic microwave background. That's the CMB. Here's the guys who did it. They both got physics Nobel Prizes for this. What they were doing, they weren't interested in astronomy. They were testing antennas. This is a great story. And everywhere they pointed their antennas, trying to test them, they got the same result. It seemed like there was a background radiation field that was very cold, under 3 degrees Kelvin. And they thought, geez, these antennas must be really not working very well. But they've kept doing this for weeks and months and finally realized it was real. This is the cosmic microwave background. Now, it turns out that this is taken by the Big Bangers as the remnant of the Big Bang, because when you do the models of the Big Bang, 13.8 billion years after the Big Bang, the universe will have expanded significantly, and the temperature is supposed to be just short of 3 degrees Kelvin, which is exactly what they observed. And so the two guys who discovered it got the Nobel Prize for it. Incidentally, this is one of the great parts of the story. Both of these physicists were very smart and very astute, but number one, they were not looking for the cosmic background radiation. And number two, when they found it, they did not know what it was. And yet they still got the Nobel Prize because the whole idea was they made a huge discovery, not so much that they didn't understand what it was they got. You know, sometimes it's better to be lucky than good, or I guess be really good at what you're doing in case you get lucky. I don't know, figure out your own moral of the story there. But anyway, the cosmic microwave background, here's what it looks like. This is an all-sky diagram showing you what it looks like. It's almost completely uniform except for these tiny temperature differences. They're like 100,000th of a degree. That's the only difference. The reason this is significant is because these tiny little temperature differences are the cornerstones for the first stars that were born in the history of the universe, and those formed the first galaxies, including the Milky Way, which happened something like maybe 600 million years after the cosmic microwave background radiation was formed. Okay, so the question then is, the Big Bangers think that this is the remnant of the Bang itself, so they think that the game's over, but the steady-staters said, in our opinion, the cosmic microwave background always existed. And that's what steady-staters usually say about practically everything. Now, one more. This is an interesting topic. Why is the sky dark at night? This is called Olber's paradox. And if you know, this is a real image, of course, of galaxies and in the sky. Notice that between the stars and the galaxies, there are dark areas. And you're saying, of course there are. We can see that. Thank you for pointing that out. But that is crucial. And the point is, if I were to ask you why the sky is bright during the day, you'd probably say because the sun's up. And we'd all agree on that. But if I asked you why the sky is dark at night, you'd be tempted to say because the sun has set. And it turns out it has nothing to do with that. In other words, what it has to do with, and I'll tell you why in a minute, it's that there are these dark patches between things like galaxies in the real sky. Now let me show you why it's so important. Olber's paradox is sort of like a forest. Imagine if you're in a forest and the trees are all over the place, and no matter what direction you look, notice we're looking at all directions here. All we see is a tree. We can't see anything beyond the trees. Let's translate that idea to the sky. Here we are on the Earth, and we're looking in various directions, and we keep running into stars. And the question is it possible to imagine a sky where we would see nothing but stars? Here, let me show you what that means. In other words, is it possible to have a sky like this, where in any direction that we look, we see a star. And this extends in all directions, this way, and this way. And no matter which direction we look, no matter how far we look, we would eventually run into a star, and it would look like this. And the only way that can happen is if the universe is infinite. In other words, there are stars without bound in all directions, and then you get a sky that looks like this. But remember, our sky does not look like that. It looks like this. The real sky has dark patches between stars and galaxies, and which shows the universe is finite. Are you guys with me? It's not infinite, because if it were infinite, there wouldn't be any dark patches in this sky. The fact that the universe is finite means it had a beginning, and that's because the night sky is dark. Now, which of the two models is finite, the Big Bang, and which one has a beginning, the Big Bang? The steady state is in real trouble. Here's the summary of our ball game we just played. We looked at Hubble's law, and both Big Bang and steady state did okay on that one, but quasars, which were a large-scale change in the universe, definitely created doubts about the steady state, which says that such things cannot exist. By definition, that's their own definition. Now, the Big Bang has no problem with quasars. The cosmic microwave background is the remnant of the Big Bang, according to the Big Bangers. It's the smoking gun, so they love it. The steady state says the Big Bang, the cosmic microwave background always was, so it's not a problem. But Olber's paradox kind of seals the deal here. It says the universe is finite, and the steady state says it's not. It's infinite in both directions, and that means that we've got, the score is 4 yeses and for the Big Bang and 2 no's for the steady state. That's why the steady state has fallen out of favor in the last 20 years, as a matter of fact. And the winner is the Big Bang. That's where most of the discussion is about. Now, there's still lots of things to talk about here. We're almost done here, but I wanted to mention a couple of things. We still don't know what dark matter is. We talked about it in connection with galaxies. It was discovered, 40 years ago, folks, and we still have no idea what this is. And its role in the origin of galaxies appears to be huge. It makes up at least 90% of the total mass of galaxies like our own and others, and yet it's still not clear what this is. Dark energy is even a bigger mystery because it composes more of the universe. This thing was discovered 20 years ago. We still don't know what it is, have no idea really what it is, to be honest about it. Its role in the acceleration of the universe. Remember, the expansion of the universe is observed to be accelerating, and dark energy is believed to be the culprit, and yet we don't know what it is or how it works. These are the 2 greatest mysteries. Oh, by the way, the destiny of the universe. If dark energy behaves the way we think it does, the universe will expand forever because the acceleration of the expansion will continue. But this is still a question mark, frankly. And the 2 greatest mysteries in the universe, remember, these make great multiple choice questions. The 2 greatest mysteries in the universe are dark energy and dark matter. Keep that in mind. Oh, and here's the chronology. I threw this together just to give you a summary of the way to think about what's going to happen in the universe. Remember, in about 800 million years, the Earth will die from a runaway greenhouse effect because the sun will have increased in luminosity by 10%. That'll be enough to trigger the oceans, and we'll turn into Venus. So isn't that cheery? Now, the other thing is, a close galaxy pal of the Milky Way is called the Large Magellanic Cloud. That thing is on a trajectory to collide with the Milky Way in about 3 billion years. That should take both galaxies out. In other words, the Milky Way will not be functioning the way it does now. It'll look quite different. There won't be a lot of star birth going on. It'll be a catastrophe. Sorry. Assuming that anything survives that collision, the bigger Andromeda galaxy, which is more our size, in about 4 billion years, is on a head-on course to collide with whatever is left from the earlier collision, also with the Milky Way. That will certainly destroy both galaxies. And what we mean by that is they'll turn into elliptical galaxies. They'll have no gas or dust. There won't be any star birth. It'll be basically a really static situation for the rest of eternity. Now remember, the sun is still chugging away, burning hydrogen into helium all this time. And it's going to do that for at least 5 billion years longer. So the sun will be around. Remember, the Earth will be long gone when these collisions occurred, but the sun will still be around functioning just about like it does today and a little bit brighter. And so we don't know what will happen to the sun. It could get ejected from the galaxy, which is a cheery thought, or even worse, it could get tossed into the accretion disk. Stuff like this is possible, and it's impossible to say right now, but something like that may happen. And then the bottom line is the universe will probably expand forever if dark energy works the way we think it does. Sounds like a lot of fun, doesn't it?